In this chapter, we focus on the data side of machine learning. The main idea is simple. Better datasets usually lead to better models. So we need to treat data as a first-class engineering problem. A model can only learn from what you give it. So even huge compute budgets cannot compensate for poor data. Dataset engineering is about building the best possible training set within your practical limits. As it becomes harder to train frontier models from scratch, more companies differentiate through their data pipelines. That means more work on collecting, cleaning, and organizing data, along with the people and infrastructure to support it. What used to be an occasional side task is now its own discipline. Many teams have dedicated labelers, dataset builders, and quality engineers because data preparation is too important to leave to chance. There are many more datasets and techniques than there used to be, so the space can feel overwhelming. This chapter gives you a practical map for navigating that landscape and making good dataset choices. We start by asking what data you need, how much of it you need, and what quality means for your task. Then we look at generation and processing, keeping in mind that these steps often loop back into one another rather than happening in a straight line. Pre-training and supervised fine-tuning use different measures of scale and different dataset properties, but the same curation mindset applies. Here we focus on post-training data, since that is the most relevant for application developers, while still borrowing useful lessons from pre-training when they help. There are tools and workflows that can automate pieces of the job, and those matter. But dataset engineering is still demanding, repetitive work, so it helps to expect real effort rather than a fully automated solution. In this section, we'll look at a shift in how people improve AI systems. Instead of only changing the model, we'll see why better data has become just as important. The main idea is that AI progress can come from either improving the model or improving the data. Data-centric AI puts the spotlight on the dataset itself. We'll separate the two approaches first, so the contrast is easy to see. Model-centric work focuses on the algorithm and the network design. The goal is to squeeze out better performance by changing the model itself or how it is trained. Now let's flip the perspective and ask what happens if the model stays fixed. Data-centric work tries to get more value from the data. That can mean cleaning labels, adding useful examples, or building data sets that let a simpler model perform much better. Traditionally, benchmarks asked who could train the best model on a fixed dataset. More recently, the question has often reversed. Given a fixed model, which dataset produces the best result? That 2021 competition made the idea concrete. Participants improved the same base dataset by correcting mistakes, covering edge cases, and expanding the data. The lesson is that small data changes can have a large effect. Later competitions push this even further, evaluating entire datasets by the performance of a standard model trained on them. That gives researchers a way to compare datasets directly, not just models. The key takeaway is that model quality and data quality are not competing ideas. In practice, the best results usually come from improving both at the same time. In this section, we look at how the right data shapes what a model can learn. Good curation can improve capability and safety, while bad data can introduce bias, errors, and wasted effort. Data is not a complete solution to model problems, but it is often a major part of the fix. When the data is strong, the model learns better behaviors. When it is poor, the model can become less reliable and more biased. Curation is not just collecting examples. It requires understanding how the model learns and what resources you have. In practice, dataset builders need to work closely with model developers, and in larger organizations, these may even be separate roles. The right dataset format depends on the training objective. Self-supervised fine-tuning uses sequences. Instruction fine-tuning uses instruction response pairs. Preference fine-tuning uses ranked responses, and reward models can use either rankings or scored examples. A model learns from the behaviors present in its training data, so the data has to demonstrate the skill you want. That becomes much harder for complex abilities like reasoning step by step or using tools, which is why the next examples matter. First, let's look at chain of thought. The key idea is that if you want a model to reason step by step, you need training examples that actually show that step-by-step reasoning. Hot prompting encourages a model to reason through a problem before answering, and fine-tuning data can teach the same pattern directly. The important point is that including step-by-step solutions can substantially improve performance on reasoning tasks. Writing a final answer is easy, but writing a trustworthy reasoning trace takes much more effort. That is why COT datasets are valuable but relatively rare compared with standard instruction data. This example contrasts a direct answer with a step-by-step response. Notice how the second prompt explicitly asks for reasoning, and the answer shows the intermediate arithmetic that the model should learn to imitate. Because those explanations are expensive to produce, chain-of-thought datasets are not as widely available. That makes them especially useful, but also harder to scale. Now let's switch to tool use. Here, the goal is not just to answer directly, but to teach the model how to take actions that accomplish a task. Tool use data often comes from domain experts because they know what tasks matter and what steps are involved. But expert descriptions can miss details, so observing real workflows is often necessary to capture the full process accurately. What is efficient for a person is not always efficient for an AI system. A human might click through a website, while a model may work better through an API, which is why synthetic simulations are often used to create better training data. Tool use can require a different message structure than ordinary conversation. Instead of a single response turn, the model may need to send one message to a tool and another to the user, so special chat formats are sometimes required. For conversational systems, you need to decide whether the model should learn from single-turn data, multi-turn data, or both. Multi-turn examples are important when tasks require clarification, corrections, or back-and-forth problem-solving. Single-turn data is simpler to collect, so it is usually easier to obtain. Multi-turn data is more realistic, but often takes custom scenarios and more effort to gather well. Curation is not only about adding new examples. It can also mean removing examples that teach the wrong behavior. In this case, the problem is a chatbot that gives unwanted extra advice instead of simply answering the user's question. Once the issue is found, you can remove the problematic examples and replace them with better ones. that helps the model unlearn the unwanted habit and learn a cleaner response style. Different tasks and training stages need different data mixes, but the core criteria stay the same. Good curation balances quality, coverage, and quantity. A useful way to remember this is to think of data like ingredients in cooking. Quality means the ingredients are good, coverage means you have the right mix, and quantity means you have enough of them to make the recipe work. In this section, we focus on why data quality matters more than sheer quantity. You'll see that good data is not just clean data. It is data that fits the task, stays consistent, and helps the model learn reliably. A smaller dataset can outperform a much larger one if the larger set is noisy, irrelevant, or inconsistent. That's why careful instruction curation can matter more than volume alone. The Lima result makes the same point. A carefully curated set of examples can produce surprisingly strong alignment. But there is a trade-off. Too little data can reduce robustness in real-world use. The Llama 3 team found that human annotations can be error-prone, especially for subtle safety judgments. That is why teams often add AI-assisted tools to improve annotation quality and reduce inconsistency. So what does high quality actually mean? In practice, it means data that supports the job you want a model to do, and it usually shows up through several useful properties rather than one single rule. First, the data has to be relevant to the task. If you're training a model for modern legal questions, old legal texts may be interesting but not necessarily useful. Relevance means the example should come from the same domain and problem you want to solve. If the target task is historical law, then those older texts become highly relevant. Next, the annotation should match what the task requires. A creative task needs creative labels. A factual task needs factual ones. And if the output must include both a score and a justification, both should be present. This is why aligned is a better word than simply correct. The right answer depends on the objective. Sometimes the best annotation is concise, and sometimes it needs extra explanation. A response can be accurate and still miss the point of the task. The label should reflect what the user or training objective actually needs, not just what is factually true in isolation. Another key property is consistency. If two annotators look at the same example, they should not produce wildly different labels, or the model will receive mixed signals. Inconsistent scoring makes learning harder because the model cannot tell what the label truly means. Clear and stable annotations help the model learn a cleaner decision boundary. That is why annotation guidelines matter so much. They help different annotators apply the task rules in the same way, which improves both alignment and consistency. Data also has to follow the format the model expects. If the structure is messy or inconsistent, even good content can become harder for the model to learn from. This often means stripping away tags, extra spaces, straying new lines, and inconsistent number formats. Small formatting problems can act like noise and interfere with training. The next property is uniqueness. Repeated examples can bias training and can also create contamination, so you want enough variety for the model to generalize well. Some duplication may be acceptable depending on the use case, but too much can distort the data distribution. So the goal is not zero duplicates at all costs, but enough uniqueness for the task. Finally, data must be compliant with the policies and laws that apply to your project. Good data quality is not just about performance. It also includes legal and ethical constraints. For example, if protected personal data is not allowed in training, then it should not appear in the dataset. Compliance has to be checked before training starts, not after. The main takeaway is that high quality is task dependent. Before collecting data, decide what these characteristics mean for your project, because the techniques in this section are designed to produce data that meets them. In this section, we're looking at coverage, whether your training data actually matches the kinds of problems your model will face. The main idea is simple. If the data is too narrow, the model will be too narrow too. Your training set should reflect the full spread of user needs, not just the easiest cases. That means capturing different ways people ask questions, different formats, and different usage patterns so the model can generalize well. If some users write long, detailed prompts and others write very short ones, both should appear in the fine-tuning data. The same is true for typos and for multiple programming languages when those are part of the real workload. The right diversity depends on the application. A translation system may care less about domain variety, while a global product chatbot needs linguistic and cultural breadth much more. For chatbots and other general-purpose systems, the dataset should span topics, styles, and output formats. The key warning is that more heterogeneous data is not always better, so diversity still has to be balanced with quality. Llama 3 is a useful example because its gains came mostly from better data and more training, not from a major architecture change. The paper also shows that data mix matters across pre-training, supervised fine-tuning, and preference fine-tuning, so each stage deserves its own analysis. Domain diversity shows up in all three training phases, but does not mean exactly the same thing in each one. Post-training also adds other axes, like response length, number of turns, and whether the data is human-generated or synthetic. This table makes the phased differences concrete. Notice that pre-training and fine-tuning use different proportions of general knowledge, math, coding, multilingual data, and specialized examples, because each phase is optimizing a different behavior. One striking pattern is that math, reasoning, and code make up a large share of the earlier training stages. The takeaway is that high-quality technical data can disproportionately improve reasoning, especially when the model is annealed on it carefully. By contrast, preference fine-tuning uses much less code and math. That makes sense because at that stage the goal is not to teach the model new technical skills, but to shape responses toward realistic user preferences. So how do we pick a data mix? Start with the real usage pattern, then use experiments to test candidate mixes. A common strategy is to train smaller models first and use those results to estimate which mix will work best at full scale. This experiment isolates an important lesson. High quality alone is not enough, and diversity alone is not enough either. The most reliable gains come when the data is both diverse and high quality at the same time. The bars in the figure compare models trained on different data properties. What you should notice is that the strongest result comes from combining both properties, which visually reinforces the idea that coverage and quality work together. This caption closes the example. A 7B model trained on data that is both high quality and diverse outperforms models trained on only one of those dimensions. The figure is a compact summary of the section's main message. Let's look at how much training data you actually need for fine-tuning. The answer depends on the task, the model, and your budget, so we'll build the intuition step by step. There isn't one universal number here. Some models can learn from a single example, while other projects use millions of examples, so the right amount depends on the situation. Even millions of examples is small compared with training a foundation model from scratch. Once you think in tokens, the scale becomes enormous. Trillions of tokens for pre-training versus far fewer for fine-tuning. There is an important caveat here. Sometimes you should compare fine-tuning against training from scratch, especially when your dataset is very large. Fine-tuning is usually more efficient, but it is not automatically the best choice. With enough data, training from scratch can sometimes win, because pre-training may make the model less adaptable, a problem called ossification, which is more common in smaller models. Beyond quality and diversity, there are three more things that shape how much data you need. First, the fine-tuning method itself. Different fine-tuning methods need very different dataset sizes, so the choice of method changes the data requirement right away. Full fine-tuning can give the best results, but it usually needs far more data than parameter-efficient methods like LoRa. With only a few hundred or a few thousand examples, PFD is often the better starting point. Next, think about the task itself. Some problems are simple and repeatable, while others require much richer supervision. A basic sentiment classifier usually needs much less data than a complex question answering system over financial filings. The harder the reasoning and the more variety in the inputs, the more examples you'll typically need. The starting point of the model matters too. If the base model is already close to your target, you need fewer examples to push it the rest of the way. A stronger base model often needs less fine-tuning data because it already knows more out of the box. That is the opposite of pre-training, where bigger models generally demand more data. With very little data, advanced models often fine-tune better because they start stronger. But once the dataset becomes large, the gap shrinks and the models end up performing much more similarly. This chart shows that pattern clearly. On the left, with only 100 examples, model choice matters a lot. On the right, with a much larger dataset, the results converge. The takeaway is simple. With little data, stronger models help more. With lots of data, full fine-tuning can make smaller and larger models behave much more alike. So the practical rule is this. If your dataset is small, start with PFT on a stronger base model. If your dataset is large, full fine-tuning on a smaller model could be a very strong option. A good workflow is to begin with a tiny, well-crafted dataset and see whether fine-tuning helps at all. If a small set already improves performance, more data is likely to help further. But don't jump to conclusions too fast. Bad hyperparameters, weak prompts, or low-quality labels can hide the benefit of fine-tuning. So you should expect improvement from a decent 50 to 100 example setup in most cases. There's also a useful way to bootstrap from lower quality or less relevant data first. That can reduce the amount of expensive high-quality data you need later. One strategy is to pre-fine-tune on broader or cheaper data, then finish with the most relevant examples. The idea is to let the model learn useful structure before the final specialization step. First, you can train on raw documents without labels, then move to the labeled question-answer pairs. This is a common way to get domain knowledge into the model before task-specific supervision. For example, if your final task is legal question answering, you can first expose the model to legal text, then fine-tune it on the smaller labeled dataset. That gives you a better starting point for the real task. Another version is to train on a nearby task first, then shift to the exact task you care about. The first stage is not perfect, but it can still make later fine-tuning easier. For sentiment analysis, tweet data can be a useful warm-up if product sentiment labels are scarce. The model learns the general task shape first, then adapts to your target domain. A third option is to generate synthetic examples first and then refine on real examples. This can help when real data is scarce or sensitive, but it takes care and good evaluation. This approach can work, for example, in medical settings, but it is harder to get right. You are effectively managing two training stages, and if the synthetic data is poor, you can waste compute and end up with a worse model. A very practical way to estimate how much more data you need is to train on increasing subsets of your current data and plot the results. The shape of that curve tells you whether more examples are likely to pay off. This figure illustrates the idea of a performance gain curve. If the line rises steeply, more data should help. If it flattens out, you are probably seeing diminishing returns. So this curve is a planning tool. It helps you estimate whether doubling your data will bring a meaningful gain or only a small improvement. In many real projects, each extra batch of training data improves performance a little less than the last one. Early examples often have the biggest impact, and later examples give smaller gains. Data quantity is only part of the story. If you expose the model to many different tasks, it usually generalizes better than if you keep showing it the same narrow pattern. That diversity can come from task type, topic variety, or output format. A model trained on summarization, question answering, JSON, and yes or no outputs learns a much broader skill set. This chart shows the benefit of task diversity. Performance improves quickly as the number of tasks grows, then begins to level off once the model has seen enough variety. The key point is that more distinct tasks usually help a lot at first. After that, additional tasks still help, but the gains become smaller. Finally, data needs are always constrained by budget. If you spend more on annotation, you have less left for compute, so the practical answer is often a compromise between the two. In this section, we'll look at how teams build datasets in practice. The main theme is not just getting more data, but getting the right data with the right quality, diversity, and legal protections. Data acquisition is the process of assembling a dataset that is large enough and varied enough for the task, without violating privacy or regulations. In practice, that can mean using public data, buying proprietary data, annotating your own data, or synthesizing new examples. The strongest source is usually data from your own application because it matches the real use case. If you can build a data flywheel from user activity and feedback, the product keeps improving from its own usage. Before building everything yourself, look for datasets that already exist. In many projects, the best result comes from combining multiple sources and acquisition methods instead of relying on just one. Here's the first step in a typical curation pipeline. Begin with a candidate dataset that looks promising. You might start by finding one dataset with about 10,000 examples. At this stage, the goal is selection. Identify data that already has the right kind of signal. Next, clean the data by removing instructions that are too weak or low quality. After filtering, the dataset shrinks, but the average quality rises. The key idea is that less data can be better if it is more reliable. Then evaluate the responses, not just the prompts, because a good instruction can still have a bad answer. This step separates good prompts from good prompt response pairs. In the example, you keep only the instructions with strong answers, which gives you a cleaner, high-quality course set. If you still have good instructions but missing answers, you can fill that gap manually. Here, human annotators create responses for the remaining high-quality instructions. That turns partially useful data into a full supervised dataset. When one topic is underrepresented, create templates before you generate more examples. This is a hybrid strategy. First, design a controlled set of instruction templates, then use a model to generate many more examples around them. It helps when you need coverage for a topic that is scarce in the original data. Synthetic data still needs human review, so the next step is annotation. After generation, annotators check and label the synthetic instructions. That final pass is what turns generated text into training data you can trust. Real dataset building is messier than this summary suggests. You often revisit the guidelines, re-annotate weak examples, fact-check labels, and adjust generation settings to protect quality and diversity. In this section, we'll look at where publicly available datasets come from and how to use them responsibly. The key idea is simple. Availability is not the same as reliability, so every dataset still needs review. These resources are a good starting point when you need data quickly. But even when a dataset is public, you should inspect it carefully and validate what's actually inside before relying on it. Before you use a dataset, check its license and trace where the data came from. A dataset may look commercially usable at the top level, but some parts can still come from sources with different restrictions. Now let's scan through a few places people commonly look for datasets. These are broad, practical starting points rather than an exhaustive list. Hugging Face and Kaggle both host enormous collections of datasets. They're often the fastest place to find something usable, especially when you want variety or a quick prototype. The next sources are useful because they help you discover data that may not be bundled into one famous repository. Search tools can uncover datasets that are easier to miss otherwise. Google's dataset search is an underrated way to find data across the web. It's especially helpful when you know the topic you want, but not the exact repository. Governments are often excellent publishers of open data. These portals tend to cover a wide range of public records, statistics, and civic information. Data.gov and data.gov.in are two major government portals with very large collections. They're worth checking whenever your project can benefit from official or public sector data. Some repositories focus on particular research areas instead of general-purpose data. That makes them valuable when your problem has a clear domain, like social science or graph learning. ICPSR is a major source for social science datasets. If you need survey data or social studies, it can be one of the strongest places to look. Some of the most useful dataset libraries have been around for years. Age alone is not a drawback if the repository is well curated and still maintained. The UCI Machine Learning Repository and OpenML are classic dataset sources. They each host thousands of datasets and remain useful for benchmarking and experimentation. Another useful category is the dataset aggregator, which helps you search across many sources at once. This can save a lot of time when you are comparing options. The Open Data Network is designed for browsing and searching many datasets in one place. It's a practical tool when you want breadth without visiting every portal separately. Sometimes datasets are included close to the tools you already use. That is convenient for experimentation, but these collections are usually smaller and more curated. Cloud providers also host open datasets, and AWS Open Data is the best-known example. It can be useful when you want data that's easy to access in cloud workflows. Frameworks often ship with small datasets you can load immediately. These are handy for demos, tutorials, and quick tests before you move to larger data. TensorFlow datasets is a good example of this pattern. The important thing to notice is convenience. You can get started quickly without spending time on manual data setup. Not all evaluation datasets stay small. Some benchmark collections are large enough to support parameter-efficient fine-tuning as well as evaluation. Eluther AI's LM evaluation harness hosts hundreds of benchmark datasets, with thousands of examples in each on average. That makes a useful source when you want evaluation data with real scale. Some domains need dedicated repositories because the data structure is different. Graph datasets are a good example, since they often require special handling and metadata. The Stanford Large Network Dataset Collection is a strong source for graph datasets. If you're working on networks or relationships, this is one of the first places to check. When the right dataset does not exist, you may need to annotate your own data. The hard part is not only labeling examples, but also defining clear guidelines for what counts as a good label. Teams often find that annotation guidelines are harder than the labeling itself. Without precise instructions, people, or models, will disagree about what a correct or high-quality response actually is. The same standards you use for annotation should also guide evaluation data. That's why careful evaluation design matters so much and why good evaluation examples can sometimes become seeds for more data generation. In this section, we'll look at two ways to create more data when real data is scarce: augmentation and synthesis. The key difference is whether we start from real examples or generate new ones from scratch. Data is one of the hardest parts of building AI systems, alongside compute and talent. That is why so much effort goes into generating data programmatically instead of collecting everything by hand. There are two main approaches here, and they solve slightly different problems. One transforms existing data, and the other creates new data that only needs to resemble the real thing. Data augmentation starts with real data and creates new examples by making safe changes to it. If you flip a cat image, it's still the same cat, but now the model sees another valid training example. This is the basic idea. Keep the underlying label or meaning, but vary the surface form. That helps a model become more robust without needing a brand new source example every time. Data synthesis goes one step further. Instead of modifying a real example, you generate a new one that imitates the patterns of real data, like simulated mouse movement on a web page. So augmented data is derived from real data, while synthetic data is generated to look real. In practice, people sometimes use these terms loosely because both methods are really about automating data creation. This idea is not new. Software engineers have long used fake data generators like Faker and Chance to test systems with realistic-looking names, addresses, and phone numbers across many formats. What changes with AI is the complexity of the data we can generate. Now we can synthesize things like notes, contracts, product text, images, and even video-like content that closely resembles human output. Synthetic data can reduce pressure on human-generated data, but it usually does not replace it completely. In many cases, the best results come from mixing real and synthetic data rather than choosing just one. In this section, we look at why synthetic data is useful in practice. The main themes are scale, coverage, quality, privacy, and model distillation. Synthetic data is attractive because it can improve the data mix in several ways at once. It can increase quantity, expand coverage, improve quality in some settings, protect privacy, and even help transfer behavior from one model to another. First, synthetic data lets you create more examples than you could collect from the real world. That matters whenever training data is scarce or expensive to obtain. This is the simplest use case. Generate lots of data at scale, so models have more to learn from. It is especially useful for rare or hard-to-capture situations, like unusual weather, deep-sea conditions, or car accidents. The next goal is not just more data, but better targeted data. Here, synthesis helps fill gaps in the dataset, so the model sees cases that real data may miss. You can generate examples with specific properties, such as very short or very long text, toxic language for a detector, or safe examples when the real data is harmful. It also helps create adversarial examples and rare classes, which is useful when the dataset is imbalanced. A good example is using language models to generate test sets for many different behaviors, from personality and politics to ethics and bias. The key point is that model-written datasets can sometimes match or even beat human-written ones for these kinds of evaluations. So the practical idea is simple. Synthesize the cases your existing data underrepresents. Coverage is about making the training or evaluation set more complete. Synthetic data is often assumed to be lower quality, but that is not always true. In some tasks, an AI system can produce cleaner or more useful data than humans can. This can happen when people have limitations that affect the data they produce, while models can be more systematic. Tool-use data and highly complex math problems are good examples where AI-generated data may be stronger than human-generated data. Another useful case is preference data. Human ratings can vary with mood and personal bias, while AI-generated preference labels can be more consistent and easier to control. Synthetic data also matters when real records are too sensitive to use. In those settings, synthetic examples let you train models without exposing private information. This is especially important in healthcare and insurance, where real records can contain protected personal information. Synthetic patient records, or claims, can support model development while reducing privacy risk. The final reason is model distillation. Here, you use one model to generate data that teaches a smaller or cheaper model to behave similarly. The goal is to copy useful behavior from a stronger model into a faster or less expensive one. Synthetic training data from the original model makes that transfer possible. So these 5 reasons are only the beginning. As synthetic data becomes more useful, more models are trained on it, and more synthesis methods continue to appear. In this section, we'll look at the older ways people have generated data before modern AI took over. The key ideas are rule-based generation and simulation, and both still matter today. Data synthesis has been used for years in fields like software testing, gaming, and robotics. In games, this is often called procedural generation. Algorithms create levels, maps, items, and characters automatically, and many of those same ideas transfer directly to AI. Traditionally, data synthesis came from 2 main approaches: rule-based methods and simulation. We'll review both first, then compare them with newer AI-driven synthesis later in the section. First, let's start with the simplest approach. Rule-based synthesis uses templates and predefined rules to generate examples that follow a known structure. Here the idea is straightforward. Define the structure once, then fill in the fields with generated values. A tool like Faker can populate realistic-looking transaction details without needing real records. This template shows the skeleton of a synthetic transaction. Notice that every field has a slot for generated content, so you can create many examples while keeping the same schema and format. That matters in sensitive domains like fraud detection, where real transaction data may be restricted. Teams often train and validate on synthetic data first to test whether a model is even feasible before touching private records. Templates are useful far beyond transactions. They can produce invoices, contracts, forms, or even math expressions, which is why they're also useful for training models on structured symbolic problems. Another common trick is to transform real examples instead of inventing new ones from scratch. Small changes like rotation, cropping, or scaling preserve the label while making the training set more varied and robust. The same idea works for text when the meaning stays the same. Replacing a word with a close synonym can create a new training example without changing the sentiment or label. You can also use this kind of augmentation to reduce unwanted bias. If your data overconnects certain jobs or traits with one gender, swapping those words helps balance the training distribution. These examples show how augmentation can change surface form while keeping the core sentence usable. The goal is not to rewrite reality, but to make the model less dependent on narrow, biased patterns in the data. To find replacements, you can use a synonym dictionary or use embeddings to locate nearby words in semantic space. And once you move beyond simple substitutions, AI can help rephrase or translate examples to create richer variants. A more aggressive form of augmentation is perturbation, where you intentionally add noise or tiny changes. Sometimes those changes reveal how fragile a model is, because even a very small change can cause a wrong prediction. Used carefully, perturbation can make models stronger. Training on corrupted or altered data helps the model handle real-world variation, which is why benchmark sets like ImageNet-C and ImageNet-P were created. Text models use this idea too. Replacing a small fraction of tokens with random words during BERT training helped improve performance slightly, showing that controlled noise can act like regularization. For images, augmentation can be much more sophisticated than simple flips or crops. Companies can synthesize variations that cover missing corner cases and reduce hidden bias in the data they use to train models. Now let's switch to the second traditional method, simulation. Here, instead of collecting data in the real world, we build a virtual environment and generate the outcomes there. Simulation is especially useful when real experiments are expensive or unsafe. For self-driving systems, for example, it's much better to test unusual road events in a simulator than on an actual highway. Robotics uses this a lot as well. You can try many joint movements in simulation keep the successful ones, and use those examples to teach the robot what works. That is the big advantage. You can run many experiments cheaply and safely. But simulation is still an approximation, so success in the virtual world does not guarantee success in the real one. Simulation is also useful for training agents to use tools. You can generate candidate action sequences, test them, and then label the best successful sequence as the answer the model should learn. Another strength of simulation is rare event generation. Finance, manufacturing, and climate science all need examples that are hard to observe directly, so synthetic scenarios help models learn from possibilities they might otherwise never see. So the traditional techniques are powerful, but they have limits. The next step is AI-based synthesis, where models can generate realistic data at much larger scale and with more flexibility. In this section, we look at how AI can create training data instead of just consuming it. You'll see several synthesis patterns, plus the main risks and ways to verify quality. The important idea here is breadth. There isn't just one way to synthesize data with AI. We'll focus on the most useful patterns, not an exhaustive catalog, so you can recognize the main tools and when to use them. One powerful use is simulation. Instead of making a real API call, an AI model can imitate the expected outcome, which is useful when calls are expensive, slow, or inconvenient to run at scale. AI can also stand in for human behavior. In games and other interactive settings, self-play lets a model generate huge amounts of experience quickly by competing against itself, which is why it has been so effective for systems like AlphaGo and game-playing bots. This same idea extends beyond games. If you need negotiation, customer support, or other agent interactions, you can script two model roles against each other and study which strategies work best. Another major synthesis trick is transformation rather than generation from scratch. If the model can paraphrase or translate well, you can turn one example into several new training examples while keeping the same underlying meaning. Here, we start the list of paraphrases for the same intent. The point is to create variety without changing the user's goal. This version changes the wording, but not the meaning. It is still a password reset request, just expressed in a more natural and formal way. This is another paraphrase example. A good synthetic dataset should include multiple phrasings that a real user might actually type. This asks for the same help, but from a slightly different angle. It broadens the surface form while keeping the task label stable. The third item continues that diversification. Rewriting examples like this can make a model more robust to different user wording. This version is shorter and more task-like. Together, the three examples show how paraphrasing can expand a dataset without collecting new labels from scratch. A good example is MetaMath, where the authors rewrote existing math problems in many ways to create a much larger dataset. The key result is that careful rewriting can improve performance even more than simply scaling model size. Translation is especially valuable when a language has little online data. By translating from a well-resourced language into a low-resource one, you can bootstrap training data for languages like Quechua or Lao. Back translation is a practical quality check. If translating into another language and then back again produces a very different sentence, that often means the original translation lost meaning. AI can synthesize programming data in the same way it handles human language. Code translation and related techniques are a major reason synthetic data became so important for models like Llama 3. A useful pattern is back translation for code. First, the model explains code in natural language. Then it tries to reconstruct code from that explanation. Only faithful reconstructions are kept for training. Synthetic data can help at both stages, but it is used far more in post-training. That makes sense because post-training often needs curated instruction and preference data, while pre-training is trying to absorb broad knowledge from the world. Once AI-generated text starts flooding the internet, models may already be learning from synthetic content indirectly. That is one reason large synthetic corpora, like Cosmopedia, have become a serious part of the data conversation. Preference data is expensive to collect, so AI judges are often used to rank candidate responses. The important detail is bias control. Researchers may ask the judge twice with swapped order to reduce first position bias and keep only consistent comparisons. Now that we've seen the broader landscape, the next step is instruction data. That is where synthetic data becomes especially practical for supervised fine-tuning. Instruction fine-tuning is where synthetic data becomes very concrete. We'll look at how to generate instructions, responses, and complete instruction-following datasets. There are several ways to build these datasets. You can synthesize instructions, synthesize responses, or mix human and AI labor, depending on which part of the task is harder to produce well. This marker separates the next idea in the workflow. We are moving from the general setup to the specific strategies for generating coverage and diversity. A practical way to generate instructions is to start from a topic list or a set of templates, then sample multiple examples from each one. That gives you coverage, and AI can even help invent the topics and templates in the first place. This is another separator in the list. The lesson here is that instruction synthesis is often organized as a repeatable pipeline rather than a one-off prompt. Once you have an instruction, you can ask the model for more than one response. That makes it possible to create richer dialogue data or to compare alternative answers later in the pipeline. UltraChat is a good example of this approach. The authors first generated topics, then subtopics, and finally full instructions and responses, which gave them a structured way to build a large dialogue dataset. Alpaca followed a similar pattern at a larger scale. A small seed set guided a much bigger synthetic instruction corpus, showing how little high-quality data can seed much more of the same kind. This figure shows the basic idea visually. A seed example on one side and a newly generated task on the other. The important thing to notice is how the synthetic task mirrors the structure of the seed while covering a new instance of the same pattern. This caption reinforces the lesson of the figure. The training signal comes from reusing the pattern of the seed example, not from copying it verbatim. Reverse instruction flips the usual process. Instead of generating an answer to a prompt, you start with strong content and ask the model to invent prompts that would have produced it, which can reduce hallucination in the response side of the dataset. This is powerful because it can bootstrap itself. A weak model generates better instructions. Those examples improve the model, and then the improved model can produce even better data in the next round. The numbered list begins the loop. Each step depends on the previous one, so the process gradually improves the data and the model together. First, you need a small starting set. Even a weak initial dataset can be enough to train a first model that later helps generate more data. The next step uses the model itself as a data generator. That is what makes the process scalable. Now the model creates instructions for strong, existing content. This is where the high-quality text becomes the anchor, so the synthetic prompt is grounded in something already reliable. Then you close the loop by training on the newly created examples. That lets the model improve without requiring much more manual annotation. Fine-tuning on those better synthetic instructions makes the model stronger. The process is iterative, so the dataset and the model can both get better over time. This final step repeats the cycle. In practice, the value comes from multiple passes, not just a single round of generation. You keep iterating until the model reaches the quality you need. This is a common pattern in synthetic data workflows: generate, filter, fine-tune, and repeat. Synthetic data is also useful for teaching longer context handling. If a model can only process short chunks today, you can build training examples that force it to use a much longer surrounding document as evidence. This bullet starts the long context recipe. The key is that we create training pairs from shorter chunks, but we keep the original long document available as context. First, break the source documents into manageable pieces. That gives you smaller units to turn into questions and answers while staying within the model's current window. This separator moves us to the next step in the pipeline. After splitting, we generate training tasks from each chunk. For each chunk, ask the model to create several question-answer pairs. That creates supervision the model can later use to learn how to search across longer inputs. This bullet separates example creation from context assembly. The next step is where the long document becomes important. Now the original long document is paired with each question and answer. This trains the model to actually consult extended context rather than relying on a short local snippet. Llama 3 is a strong case study because it combines several synthesis techniques at once. The paper shows how code translation, back translation, and new code generation can be blended into one large supervised fine-tuning pipeline. The workflow starts with a simple first step: create the problem descriptions. Everything else is built from that foundation. The model first produces a broad set of programming tasks. Diversity matters here because the goal is to cover many coding patterns rather than just a narrow benchmark style. Once the problem is written, the next step is to solve it. This keeps the synthesis pipeline moving from specification to implementation. Given the problem and a target language, the model writes code. The authors found that adding general programming rules and chain-of-thought reasoning improved the quality of those solutions. After generation, the data is not trusted blindly. It goes through a correctness pipeline so that only examples that actually work are kept for training. The next checks are programmatic. That matters because code can be tested in ways that text usually cannot. Parsers and linters catch syntax and basic static errors early, like missing imports or bad variable usage. This is a cheap but powerful way to reject broken code before deeper testing. After syntax checks, the pipeline moves to execution. That is where functional errors usually show up. Unit tests tell you whether the code actually behaves correctly. In a nice example of automation, AI can even help generate the tests that validate the code. If a solution fails, the pipeline does not stop there. Instead, it feeds the failure back into the model for repair. The revision step is crucial. The model gets the original problem, the broken code, and the error feedback, then tries again until the example passes all checks and earns a place in the dataset. Taken together, these methods form a robust synthetic data pipeline. The value is not just volume. It is the combination of generation, testing, repair, and verification. This summary starts with problem creation. From there, the workflow expands outward into solutions, tests, and verification. The first ingredient is the promptable task itself. If you can create good problem statements, you can generate a large family of downstream examples. Next comes solving those problems in multiple languages. That broadens the dataset and strengthens transfer across programming styles. This step is code translation at scale. By producing solutions in several languages, the dataset becomes more useful for multilingual code models. Once code exists, it needs tests. Otherwise, you do not know whether the examples are actually correct. Unit tests provide the objective check. They turn synthetic code from a guess into a verified training example. If the tests fail, the system gets another chance. That feedback loop is what makes the pipeline practical at scale. Repairing failures is part of the data generation process, not an afterthought. It helps push the synthetic code toward reliability instead of accepting the first draft. The pipeline also includes translation across languages. After translation, the code still has to prove itself by passing tests. This is a very strong filtering strategy. Translate the code, run the tests, and discard anything that no longer behaves correctly. The final ingredient is explanation. Good code models should not only write code, but also explain it clearly. Here the model writes explanations and documentation for code, then verifies those explanations by back translation. That helps keep the pros faithful to the actual program behavior. Using the full pipeline, the authors generated an enormous amount of usable training data. The scale matters, but the quality control steps are what make that scale meaningful. Now we switch from generation to validation. Once you synthesize data, you still need a way to decide whether it is actually good enough to train on. The basic idea is simple. Synthetic data should be judged the same way we judge model outputs. Where possible, use functional tests. Where that is impossible, use AI judges or scores. Even though we are discussing synthetic examples, these verification ideas are more general. They can help you evaluate training data from many sources, not just AI-generated text. A big reason coding data is popular is that it can be checked automatically. The same logic explains why many synthetic datasets focus on code. If you can execute it or back-translate it, you can verify it. When functional checking is not available, an AI verifier becomes the next best option. You can ask for a score, a binary decision, or a judgment against explicit quality criteria. If factual consistency matters, use fact-checking or inconsistency detection to remove likely hallucinations. This is especially important for long-form text, where errors can be subtle but damaging. Sometimes the question is whether synthetic data looks like the real target distribution. In that case, you can use a detector or classifier as a proxy for realism and discard examples that are too easy to spot or too low quality. You can also filter by topic and by outliers. If an example is off-topic or unusually strange compared with the rest, that is often a sign it should be removed. Not every filter needs a model. Simple heuristics like length limits, repetition checks, and source filters are often effective and easy to apply at scale. This bullet introduces the practical examples of filtering used in early synthetic datasets. The next few items are concrete rules that remove weak examples. Repeated examples add little value and can even skew training. They're usually one of the first things to remove. This separator leads to another common filter, length. Too much or too little text can both be a problem. If instructions are extremely long or extremely short, they often become unusable. Length thresholds are a simple way to keep the dataset in the range your model can actually learn from. This bullet separates one more quality issue. Sometimes different outputs hide the same underlying instruction, which creates inconsistency. If one instruction appears with conflicting responses, that can confuse the model. These collisions are often filtered out, so the dataset stays internally consistent. This final filter removes a particularly bad pattern, copying the input back as the output. That usually means no real learning signal is present. If the answer just repeats the prompt, the example is not useful for training. It tells the model nothing new, so it should usually be discarded. even with many filters and scores. The real question is whether synthetic data improves the model in practice. If it does not help on the downstream task, then all the synthetic quality metrics in the world are not enough. Synthetic data is powerful, but it is not a full replacement for human data. The main limitations come from quality, imitation, collapse, and unclear lineage. It is tempting to imagine a future where models generate everything. In practice, though AI-generated data still has important weaknesses, so human data remains necessary for a lot of tasks. The first limitation is simple. Synthetic data can be bad. If the generated examples are low quality and you cannot verify them, the dataset becomes hard to trust. This old rule still applies. Reliable evaluation methods are essential because people will not build on synthetic data unless they can be confident it is good. The next risk is that a model can imitate style without really improving understanding. That means a dataset can look impressive while hiding weak factual or reasoning performance. Some imitation models learn to sound like the teacher without matching the teacher's real capabilities. They may reproduce tone and format well, but still struggle to generalize or stay factually accurate. This is especially dangerous for reasoning tasks. If a student model learns to imitate solution-shaped answers without the underlying skill, it may become more confident in wrong answers rather than better at solving problems. A deeper risk is what happens when synthetic data is reused over and over. Over many generations, the training distribution can drift and rare events can disappear, which can damage the model. Researchers call this model collapse. The concern is that repeatedly training on generated outputs can introduce irreversible errors and make the model forget less common patterns. One intuitive explanation is frequency bias. The model keeps producing the most likely patterns, so the data becomes more ordinary over time and less representative of the rare cases that matter. Some studies suggest collapse is much less of a problem if synthetic data is mixed with real data rather than used alone. The exact ratio is still an open question, so there is no universal recipe yet. At the same time, large synthetic datasets can be surprisingly effective in practice. Some models train well with heavy synthetic mixtures, which tells us the issue is not whether synthetic data works, but how it is used and whether the pipeline is disciplined. Bias is another serious concern. If the original model already has skewed behavior, generating new data from it can preserve and even amplify those biases through a feedback loop. The final limitation is less visible but very important: lineage. When AI generates data, it can become hard to know where that data really came from, and that creates legal and evaluation risks. If a model's training data is unknown or mixed with copyrighted material, the synthetic output may inherit that problem. So even when the data looks new, its source may still matter a great deal. Lineage also matters for benchmarks. If a generator has already seen the benchmark you are using for evaluation, your results can look better than they really are, which undermines trust. So the big picture is this: synthetic data is useful, verifiable, and powerful, but still needs careful control. Next, we move to a case where synthetic data is not just helpful, but essential: model distillation. In this section, we'll look at model distillation, how a smaller model can learn to behave like a larger one. The key idea is not just compression, but transferring useful behavior from teacher to student. Model distillation, or knowledge distillation, trains a smaller student model to imitate the outputs of a larger teacher model. In effect, the large model's knowledge is compressed into a form that is easier to deploy. The usual motivation is deployment. A large model can be expensive to run, while a distilled model is faster and cheaper. Distillbert is a good example. It cuts the size substantially, keeps most of the capability, and runs much faster. A student can be trained from scratch, or it can begin from a pre-trained model and be fine-tuned on teacher-generated examples. Alpaca is a well-known case where a smaller llama model learned from outputs produced by a much larger model. There is an important limitation here, though. Distillation is only possible when the data and the model license allow the teacher's outputs to be used for training. Not every model can legally be distilled. Some licenses explicitly prohibit using a model's outputs to train another model, especially if a new model competes with the original. Synthetic instruction data is often paired with adapter methods like LoRa. The result can be much cheaper inference, although the real question is whether the distilled model still performs well enough for the task. It's worth separating two ideas: using synthetic data and doing distillation. Distillation means the teacher is the standard the student is trying to match, but synthetic data can also be used to train a model that eventually exceeds the teacher. That's why some modern systems use a stronger model to generate training data for an even larger student. In cases like Nematron 4, the student improved beyond the model that helped generate its instruction data. The last point is an important caution. Self-generated data does not automatically help, and it can even hurt. The models improve when the synthetic data is filtered and verified, so quality control becomes part of the training loop. Now we'll look at data processing, how raw data is cleaned, filtered, and prepared for a specific use case. The main idea is that the best workflow depends on both quality and efficiency. There is no single universal recipe here. Different tasks need different processing steps. So this section focuses on practical reference ideas rather than a fixed pipeline. One of the best sources of ideas is model papers that describe their datasets in detail. Those papers often reveal how researchers curated, generated, and processed the data before training. Here are a few practical tips for large-scale processing. The goal is to reduce wasted time and avoid mistakes when the dataset is too large to handle casually. Once the dataset grows, even simple steps can become expensive. That is why planning the order of operations matters so much. The first optimization is to choose the order of steps carefully, based on what saves the most time and compute. If one step is costly, try to shrink the data before running it. For example, remove obvious low-quality examples before doing expensive cleaning or deduplication, whichever saves more work overall. The second optimization is to validate your scripts on a small sample before scaling up. Always test the processing pipeline on a small batch first. That lets you catch logic errors, formatting issues, and unexpected side effects before they affect the full dataset. The third optimization is to protect the original data instead of overwriting it. Avoid modifying the source data directly. Keeping an untouched copy gives you a safe fallback and makes it easier to reuse the same dataset in different ways later. There are two main reasons to keep that original copy. First, another project or team may want a different version of the data for a different application, so the raw copy remains useful. The second reason is safety. Processing bugs can damage the dataset. If a script has an error, it can quietly corrupt your data and be hard to undo. A preserved original makes recovery much easier. Before you train on a dataset, pause and inspect it carefully. In this section, we'll look at the basic statistics, the distribution of examples, and the kinds of problems manual review can reveal. First, ask where the data came from, how it was processed, and what it has already been used for. Then check summary statistics and metadata so you know whether the dataset is trustworthy and fit for your task. Next, look at distributions, common tokens, input lengths, response lengths, special tokens, topics, and languages. These patterns tell you whether the dataset matches the task you actually want to solve. You do not have to stop at simple counts. More creative statistics, like verb, object pairs, or response length, can reveal how datasets differ and can even help compare model behavior on the same prompts. This kind of plot shows which action patterns appear most often in the data. It is a compact way to see whether your examples cover a narrow set of behaviors or a broader range. The point of the figure is not just visualization, but measurement. A distribution like this gives you a simple statistic for comparing one dataset to another, or even one model's outputs to another's. Here, the shape of the curve tells you how long different model responses tend to be. Comparing those shapes can reveal stylistic differences, like one model being more concise and another being more expansive. This figure makes the length difference easy to compare at a glance. It is a reminder that simple descriptive statistics can uncover meaningful differences in generation behavior. The takeaway is that GPT-4 uses a wider variety of verb, noun pairings, and generally produces longer answers. That suggests both greater diversity in wording and a difference in response style. Now break the data down by source, time, annotator, or any other useful dimension. This helps you find patterns, outliers, and systematic differences that a single overall statistic would hide. If scores should look roughly normal, verify that each annotator follows that expectation too. Some people may give unusually short answers or consistently higher scores, and you need to decide whether to adjust for that. When examples have multiple annotations, compare them directly and compute disagreement. Conflicting labels are not just noise. They're often the best places to inspect carefully and resolve by hand. Tools help you explore quickly, but they do not replace actually reading the data. A short manual review often reveals issues that statistics miss, and that can save a lot of debugging later. Finally, sample a few examples and check whether they make sense. If you have labels, try annotating them yourself. Then compare your judgment to the dataset to test trustworthiness, uniqueness, and consistency. In this section, we'll look at why duplicate examples can distort your dataset and how to remove them. The key idea is simple. If the same information appears too many times, your model can learn the wrong lesson. Duplicates do two harmful things. They change the apparent distribution of the data, and they can contaminate evaluation. If a repeated example lands in both train and test, the model may look better than it really is. This small table shows the problem clearly. The repeated red pencil rows are counted multiple times, so the dataset makes that example seem more important than it really is. Research has shown that duplication can reduce model quality, even when most of the data is unique. And even if accuracy does not drop, you still spend extra time and compute training on repeated information. Not all duplicates look identical at first glance. In practice, you often need to think about duplication at the document, paragraph, or sentence level. Let's break those cases down one by one. This is the simplest case. The same full document appears more than once in the dataset. It is usually the easiest kind to detect. Next is a subtler kind of repetition inside a single document. Here, the document is not repeated, but a passage inside it is. For example, the same paragraph may appear twice in the same file. And duplicates can also show up across different documents. In this case, a shared fragment appears in multiple documents, such as a common quote or boilerplate text. That makes the duplication harder to spot by a simple exact matching. The definition depends on your task. You have to decide the unit of comparison and the threshold for saying two examples are the same, especially when order or partial overlap matters. Deduplication often reuses similarity techniques, and it also shows up in identity resolution, where you ask whether two records refer to the same real-world entity. Once you know that, you can choose the right matching strategy. One direct approach is to compare examples against one another. It is conceptually simple, but the cost grows quickly as the dataset gets larger. You can use exact match, n-gram overlap, fuzzy matching, or semantic similarity. The trade-off is speed. This method can become expensive when the dataset is large. A faster strategy is to group examples into buckets first. Then you only compare items that land in the same bucket, which reduces the search space. Methods like min-hash and Bloom filters help approximate this idea at scale. They are useful when exact all-to-all comparison would be too slow. Another option is to compress the data into a lower dimensional representation first. Then you can compare the reduced forms instead of the full originals. This works well when your examples are vectors, because many vector search techniques can help you find near duplicates efficiently. The reduced space makes large comparisons more practical. In practice, you do not have to build everything from scratch. There are libraries for exact matching, fuzzy matching, hashing, and text deduplication that can save a lot of implementation time. In this section, we focus on improving data quality before training. Cleaning and filtering can make a model safer, cheaper to train, and more effective. Raw data is rarely ready for training. Cleaning it helps the model learn better patterns and reduces the chance that it absorbs harmful or noisy content. A common cleanup step is stripping out markup like HTML or excess markdown. These tokens often come from scraped sources, and unless they matter for your task, they just waste space and distract the model. You also need to filter out anything your policies do not allow, including private data, sensitive information, copyrighted material, or toxic content. That often means dropping fields such as names, zip codes, or gender when they are not permitted. Filtering is not just about safety, it is also about quality. If examples are noisy, corrupted, or unreliable, removing them can improve the usefulness of the remaining training set. Manual inspection matters here because some quality problems are subtle. Looking directly at samples can reveal patterns you can turn into simple heuristics, like noticing that annotations later in a session may be less careful because of fatigue. If you have more data than you can afford to train on, filtering becomes a way to spend compute wisely. Methods like active learning, important sampling, and data pruning try to keep the examples that will teach the model the most. Now we turn clean data into the exact format your model expects. The key idea is consistency. Tokenizer, chat template, and training examples all have to match, or you can introduce hard-to-diagnose bugs. After deduplication and cleaning, the next step is formatting. Each model has its own tokenizer and chat template, so the data has to be converted before fine-tuning. If you use the wrong template, the model may train or respond in surprising ways. For supervised fine-tuning, the simplest view is instruction and response. Often the instruction can be split into a system prompt and a user prompt. And unlike prompt engineering, fine-tuning examples usually do not need long task descriptions or few-shot examples. Here is a familiar three-shot prompt for food classification. This is the kind of prompt you might use with a base model before fine-tuning, where you have to show the pattern explicitly. This prompt gives the model a pattern to imitate. Input item, then label. The few examples teach the mapping, and the final blank label is where the model is expected to answer. Notice how much of the prompt is there just to provide context. During fine-tuning, those few-shot examples become individual training pairs. Instead of one long prompt with demonstrations, You create many examples so the model can learn the task directly from data. This table shows the simpler fine-tuning format. Each row is one example, a single input and a target output. That is the core transformation from prompt-based inference to supervised training data. Once the model has been fine-tuned, you do not need the long instructional prompt anymore. The input can be much shorter, which also helps reduce token cost at inference time. After fine-tuning, the prompt can collapse to just the input format the model learned. The important thing is that this tiny prompt still matches the structure seen during training, so the model knows what to do next. This is why fine-tuning can be cost-effective. If your instruction prompt is expensive in tokens, teaching the behavior during training lets you use a much smaller prompt later. Different fine-tuning formats can lead to different results, even with the same data. It is worth experimenting to find a format that gives you the best performance for your task. At inference time, your prompt should match the format used in fine-tuning. If training used a pattern like burger, even small differences in the prompt can make the model behave inconsistently. The next few lines are examples of mismatches. These are small changes, but they matter because the model learned a very specific prompt shape during training. If you drop the arrow, the prompt no longer matches the training pattern. That missing symbol can be enough to confuse a fine-tuned model. Another example of a mismatch is adding extra text before the input. The model may not recognize that as the same task format it saw during training. Here the prefix changes the prompt structure. Even though the input still contains the same word, the model now sees a different template, which can hurt reliability. Spacing can matter too, especially when the format is very strict. If the model was trained on an exact pattern, small formatting differences can still create problems. Even an extra trailing space can change the prompt enough to matter. The takeaway is simple. Keep the fine-tuning format and the inference prompt aligned as closely as possible. Let's wrap up the main ideas from this chapter. The big takeaway is that dataset design is deliberate work. You define the behavior you want, then build and verify data to support it. Creating training data can be complex in practice, but the guiding principle is simple. Start with the behaviors you want the model to learn. Then design the dataset to reveal and reinforce those behaviors, while also treating privacy and compliance as first-class concerns. The exact data you need depends on both the use case and the training stage. Pre-training, instruction fine-tuning, and preference fine-tuning all need different data, but they share the same evaluation lens: quality, coverage, and quantity. Volume gets attention, but it is not enough on its own. A smaller, cleaner dataset with better diversity can beat a much larger noisy one, because the model learns more useful patterns from data that is both accurate and representative. When real data is hard to obtain, synthetic data becomes a powerful option. Recent AI systems can generate realistic examples well enough to support many use cases, including instruction data for fine-tuning. But generated data still needs evaluation before it enters training. The challenge is that judging AI-generated data is itself a difficult AI problem, so teams adopt it more readily when they can assess it reliably. A lot of dataset creation resists automation. You can automate pieces of generation or labeling, but you still need humans to decide what data matters, define good annotation guidelines, and catch subtle mistakes. That difficulty is also what makes the work creative. There are many valid ways to design and verify data, and the techniques in this chapter are meant to give you ideas for building datasets that fit your own problem. Once the dataset is ready and the model is trained, the next question is how to serve it well. In the next chapter, we move from data preparation to inference with a focus on latency and cost. The footnote shows how much the role of data has expanded over time. Between GPT-3 and GPT-4, the number of people involved in data work grew dramatically, which is a strong signal that data quality and data operations are now central to model building. At scale, compliance is not a side task. If you work with a lot of data, simply making sure it is handled correctly can become a full-time responsibility. Different communities define data quality in different ways, but here the useful question is narrower. Is the data good enough for the training task you care about? For fine-tuning, that usually means correct, consistent, and useful examples. Even a simple storage mistake can corrupt your dataset. If a floating point column is accidentally stored as integers, the values get rounded, and the model may learn strange behaviors from bad inputs. Uniqueness here is not just about deduplication. Data that no one else has can be extremely valuable because it gives your model information that competitors may not be able to copy. There are also other ways to cut down the need for large amounts of labeled data. Weak supervision, semi-supervision, and active learning all help you get more value from less manual annotation. Many companies talk about data flywheels because the idea is powerful. Better product usage creates better data, which improves the model, which improves the product again. The footnote is a playful reminder that this phrase has become almost mandatory in AI pitches. Data augmentation is another way to stretch limited data. The idea is to create useful variations of existing examples, so the model sees more diversity without starting from scratch. Some tasks require generated examples by definition. If you want a model to detect AI-generated content, then AI-generated content must appear in the training set. Procedural generation is a familiar example outside machine learning. Games use it to produce large, varied worlds and experiences from rules and randomness instead of hand-authoring everything. In theory, a model could generate data that helps train a better version of itself. In practice, whether that loop works reliably is still an open and difficult question. This result suggests that execution feedback can help a model repair some of its own mistakes. That is important because it shows how generated solutions can become better through evaluation and correction. The same risk appears with human annotations. If labelers use information the model does not have, they may accidentally teach the model patterns it cannot truly support, which can lead to hallucination. This idea was later developed more fully in research on recursively generated data. The warning is simple. If models train too much on their own outputs, quality can degrade instead of improve. The exact model sizes here are less important than the relationship. A smaller teacher model can still produce useful training signals for a larger student model, even when the architecture comparison is not perfectly symmetric. Finally, there are practical tools that support overlap estimation and deduplication. Those are small but important parts of keeping a data set clean, especially when you're working with large collections of data.